All right, so let's look at another examples of forced response. So what happens when you have a forced response is you have this driving force and you have the damping in this example, in the previous example too. So when you have a non-homogeneity in the differential equation, you get a particular solution. So the eventual behavior of the spring mass system is represented by the particular solution. That means completely controlled by the driven force. Okay. All right. So let's look at another example. So we have a mass of 1 gram here and K is 50. So 50 over 1, K over M. So 50 over 1 will give you W square, which is 50. And 2 lambda is actually beta over M. Beta is here actually 2. 2 over 1 is 2. So we get this differential equation and they say the external force is 41 cosine 2t. Now I'm going to walk you through this problem concentrating on more physical application. Okay, so what we do is we write the auxiliary equation here. First we solve the homogeneous differential equation and we get roots. Alpha is -1, a complex root, beta is 7. So this is the complementary solution. Okay, now we need to come up with a guess for particular solution. So the right hand side is a constant time cosine term. So your guess will be A cosine 2t plus B sine 2t. So you take both cosine and sine into account, right? So we saw that earlier when we are doing the section 4.4. Now do we have an overlap? No, right? Cosine 2t and cosine 70 different. Sine 70, sine 2t again same, different things, right? So we do not have an overlap. So we know xp. So we calculate x prime p, x double prime p, and we substitute it into the differential equation. All right, so when you substitute, you get this long expression. We group sine terms together, we group cosine terms together, and we compare coefficients of cosine on left and right. Get the equation, compare coefficients of sine and on the left and right. Get the two equations and solve, and we get the particular solution like here. Okay, then we use the initial conditions and we can get the solution, final solution for the system. So let's focus on the final system. All right, so what I highlight in blue color is the particular solution. What I have in red here is the complementary solution. Here's the question: what is the eventual behavior, or what is the limit of this solution? What is the limiting behavior? Now here, this is very interesting. When t goes to infinity, in the complementary solution, you still have an exponential decay, right? Because it takes the damping into account. So when t goes to infinity, that red color term, red part term still will approach to 0 because it will overrun by the exponential decay. E to the negative t times sine, e to the negative t will overcome, and then you get an exponential decay. So that's good. Now what happens though in this blue color part when t goes to infinity? When t becomes large, cosine and sine, do they approach to something? No, right? They behave like typical sine cosine curves which look like this. And that is exactly what you can see in this picture. See what happens. At the start, okay, you get a higher amplitude, higher displacement. Then the displacement dies out. Do you see it? Amplitude gets small. Why is that? Damping, right? That is where this complementary function part plays its role. Okay, so then it decays out. But then it really doesn't decay out to 0 because when time moves on, when time gets large, this part gets small, but this part doesn't. It doesn't get large either, but it tries to behave like a sine cosine curve combination when time goes on. Okay, so that is why we have after larger time, you can see you have this typical nice sine cosine behavior that exactly comes from this blue color highlighted term. This is the particular solution. If you plot the particular solution here, exactly you will get this part of the plot. Okay, so eventually again what we said in the previous video is true. When you have a driving force and damping, eventually the whole system will behave like the particular solution, and the whole thing comes from the driving system, the driving force. Okay, so that's the explanation. So try to digest it, try to understand the whole scenario. Now see, we started from free undamped motion, no damping, no force. Okay, remember what we got there, and then we had damping in our system but no driving force. So we discussed three cases. All in those three cases, when we have a homogeneous equation but we have damping, we approach to the rest position, the equilibrium position, or eventually the displacement is zero. So we achieve that no matter what kind of roots we have. But now, all of a sudden, we have a driving force. We have an unhomogeneity in the differential equation. So the system eventually will start behaving like the particular solution, which comes from the driving force. Okay, again, so sorry that I said the same thing repeatedly again and again, but this is very crucial. Isn't the physical explanation of what we learn in chapter 4 is beautiful, and it makes sense, right? And you will see more beautiful things in the future videos of this same section, because we are not done with the mechanical vibrations. Okay, all right, thank you.